Is it fine, Sasank, now? Let's wait for 1 minute. Is it fine?
Yes, sir, it is coming.
Is it fine, Sasank? Okay, I think good to go.
Well, let's do a test first. Can you hear me?
Yes.
And through the YouTube channel as well?
Yes, sir, it is audible in the YouTube.
Okay, great. Thank you very much. I just wanted to start by saying thank you for this opportunity. I started my career at IIT Guwahati, and I really liked my time in Assam. So I'm excited to be back and to be able to present to this group. So thanks very much for the opportunity, Sishir and others involved. Keep your questions coming. I'll try my best to answer them. Couple of things. This field has become really large, and I'm not. Uh, LLM is not my main expertise. I will go into where I have been focusing last several years. But I'll still try to answer questions as best as I can. So currently, I'm CEO of Agile Data Decisions. It's a startup based out of Houston. We are an AI company. We are particularly focused on capturing data from technical documents. So we specialize particularly in very traditional industries such as oil and gas, defense, and mining, although we are trying to get into healthcare as well. So what I'll do today is one of the things about my career is I got my bachelor's at IIT Guwahati, and then ended up with a PhD from University of Maryland at College Park. Back then, it was in speech recognition, particularly applying machine learning methods to speech recognition. The world has evolved quite a bit since then, and at every step, I have tried to evolve with it. So what I'm going to do, because I think I have lived through this whole revolution over the last 20 years, I would like to give a little bit of historical overview on how we get to LLMs. I know it may not be relevant for everybody. Some of you probably already know this, have been specializing in this, and you may know this better than me. But I would like to touch upon some historical points on how we got here in general. And then I will describe a little bit of what we have been doing at our company with our customers, especially in oil and gas and with government. And if time allows, I'll even be able to give a demo of our product. Sishir, so far so good in terms of audio?
Yes. I think you can start. Maybe. Yeah, that's
Okay,
fine.
let's screen share. Okay, Sishir, you see the screen, and also in YouTube?
Yes, sir, it is visible.
Okay, excellent. So let's get started here. So first, like I said, brief overview of how we got here. The field of machine learning is very, very old. We'll in 20 years we'll hit 100 years, because when you look at some very basic stuff, um, the perceptron, the basic unit of neural network, came in 1950s. The multi-layer perceptron, which is essentially nothing but a deep neural network, in 1960s, and a stochastic descent algorithm to train neural networks came also in 1960s. And then go forward, the terms you hear every day today: reinforcement learning, again from the 70s, back propagation from 80s, recurrent neural networks also from 80s. So what happened? Why did all this revolution not happen in in 1980s. In fact, what happened was in 90s, everybody lost interest except for a few people. So there was not much neural network going on when I started my PhD. People were trying stuff like support vector machines, etc., with mixed results. I mean, some of these statements you can trace back where the some of the ideas came from with machine having an original idea. So that's AI, Frank Rosenblatt, 1958. But I mean, even before that, Turing talked about AI and defined the rule we call the Turing definition of AI. So, but I'd really like to discuss what really went wrong back then in 80s. I mean, these type of neural networks have existed since the 60s. So multi-layer perceptron, it's a deep neural network. The problem was it easily got overtrained back in the day, and it did not generalize to large amounts of diverse training data. And some new methods such as support vector machines and tree-based methods like random forests were generalizing better to larger amounts of data, and while these type of neural networks did not. There's obviously lots of reasons why they did not. I'll not go into that, but really, when I look at this history and having lived through it, really the real breakthrough came with with one theoretical invention, which was pre-training. So typically a neural network, you go left to right. I mean, you provide some data, and here it moves through the layers, and you get your output. Hinton in 2006 flipped this whole notion around, and he said, okay, I'm going to start with visible units and generate some hidden units. And he called this restricted Boltzmann machine. Actually, I'm not sure if he called it or somebody else called it, but the idea was here, there is no direction. You can generate these hidden units from the visible units, or you can generate visible units from the hidden units. And he said, let's train this. Let's take some data. Let's say this is an image, a visible image, and we're going to train this network. You can ask the question, why? What are we training for? I mean, what are these hidden units? And the best way I understand it is you go from these hidden units to visible units. So when you're doing that, you put some random data here and you get an image. And you get a type of image that you've trained for. So, and then he put a bunch of these together where you don't have just two layers like this. You have a lot of layers. You start from some, actually, I'm supposed to have an, anyway, no worries. So let's ignore the input and output for a second. So he put multiple of, okay. He put multiple of these layers together, and we went from hidden layer to visible layer, or visible layer to hidden layer. And we trained this layer by layer, but again, he did it without giving it, without providing some classes. Let's say you have cats and dog images and you want to differentiate between cats and dogs. The whole idea of pre-training was that we were going to train this without telling it whether this is a cat or a dog. So you would go from visible layer to hidden layer without really telling it that it's a cat or a dog. So this concept of unsupervised pre-training is what revolutionized deep learning, because now once you have pre-trained a model, you can now say, okay, these are cat images, these are dog images, and now these models were generalizing very well. While I said this happened in 2006, Hinton had been working on it for 20 years. He never gave up on neural networks. And with this concept of unsupervised pre-training, he revolutionized it. And in fact, the field of speech recognition was turned around overnight with this concept. This is a misconception that deep learning first made a huge impact on image. Actually, it first made a huge impact in image recognition, sorry, in speech recognition, with these type of deep belief networks, where you first train without telling it what it is, like what speech it is. You don't tell it. You just dump thousands of hours of speech without telling it what kind of speech it is or what is being said. That's pre-training, and then you tell it what is being said, and then it fine-tunes to then build a model to understand speech. So this was one key invention, I would say one of the biggest inventions of this century, which in my opinion, led to the deep learning revolution. The second was GPUs. While all that was true, you still couldn't train these things, but then GPUs happened, and GPUs were already optimized for matrix multiplication, and much of the math of deep learning training boils down to matrix multiplication. So GPUs really help, and when you put these things together, we started to get practical generalizable models that we could use with good results. And then you could further use multiple GPUs. You could use GPUs in a data parallel way, where the data was split. The same model was put in multiple GPUs, and you put different data on each GPU, or you split the model into your whole GPU set. You build such a big model, and that's the case for something like GPT-4 Turbo, where it's splitting the model is split across multiple GPUs. Of course, you can do both in parallel. You're splitting the model across multiple GPUs, and then also having multiple instances of that, and each instance is taking some data in. So I'm going to pause here, see if there are any questions. So I think it's still the same questions. If there are any questions on what I have presented so far, please keep them coming.
Okay. Okay.
Yeah. Are there any, or shall I continue?
You can continue. You can continue. Yeah.
Okay. Okay, so now let's make our journey to large language models. Essentially, you can say it started with recurrent neural networks. Again, a very old concept. It was very simple. You have English and you want to convert to Hindi, you will, or Assamese, you would get each word in English. These are the X's, and it goes through a hidden layer and outputs a word in the output language. And you keep on moving. You have one hidden layer that feeds into the next hidden layer. So when you get the next word, it kind of remembers. There's a concept of memory. It remembers what happened before in the hidden layer. So using what happened before and what's the new word, it tries to generate the new output word. So it's a very simple network. It was not very successful because it just could not model enough. And from there, the revolution, another revolutionary concept came that was of attention. This is the attention mechanism. There's a paper called Attention is All You Need, but that's not the paper where the idea of attention came in. The idea of attention came from this paper by Bengio et al. So in here, you just take the same recurrent type of neural network, but the new thing you do is you combine the outputs of different hidden states. So you make the dependence of your output and what you're going to output more explicit on the past, rather than just imagining that each hidden layer will remember everything from the past. It's not going to remember everything. So we're going to take a more explicit model to model on how it depends on the previous words. So this was then made more complicated, where then instead of having one hidden state, you can think of splitting it into 3 hidden states. One state helps produce the next hidden states, while one models the attention. They called it key value and query. This is from the attention is all you need paper. I mean, this is one of the basic concepts in it. The whole idea is to model with more explicitness, model the context more explicitly using these three different types of hidden states. So again, each time you do this, we started from this, we came to this, then we came to this. We keep adding more and more layers, so to speak. And as we do that, we get more and more trainable parameters. And this evolved into self-attention, which is essentially this is self-attention, but this is a more explicit representation. You have the input and you have the outputs. It moves through these key and value states and query states. All of them combine to give the output. So when you this is obviously showing the inference, but you use something like stochastic descent to train this when you have a lot of training data. While this looks complicated, this is much more complicated. So when we talk about transformers or large language models, that's what we're talking about. This whole picture is just a small part here. So this is self-attention, what's in this page, and there are several different heads. Each self-attention constitutes one different head, and this whole thing is just a small part of the whole transformer. So there are many. So there are different modules here that look like this in the encoder and decoder. So this is so you can see we started with simple model, kept on making it more complicated and more complicated. We made it. We had more trainable parameters to the point that GPT-4 Turbo is so big it is trillions of trainable parameters, and you need multiple GPUs to hold it. So it's very hard for a startup company like us, small company like us, to even hold a model like this. We have enough GPUs to be able to train a model like this. So the advantages is there's much more you can do with this. There's a large number of trainable parameters and hidden states, but you also need a lot more data to train. So OpenAI used, well, they have 10,000 GPUs. We don't know exactly how many they used. And just to train those models, they're spending hundreds of millions of dollars just on training. Training ChatGPT and the GPT-4 models. So, well, I'm gonna stop here again to see if there are any questions.
I think so we can take questions at the end of the session. Yeah.
Sorry, could you repeat that?
We can take the question at maybe end of the session. Yeah.
Okay, yeah, no problem. Okay, so what do we do at AgileDD or Agile Data Decisions? We specialize in making human-in-the-loop interfaces. Our focus is to get trustable data from documents. The challenge is that while GPT models, etc., they are great, can they be used to get data from documents that enterprises can trust and make their decisions on? So our focus has been we have found that you can't really trust the data. You have to build trust. So how do you build trust? By having human in the loop, saying human says that, okay, this is right, this is wrong, and then we improve or fine tune the models to more accurately capture data from documents. And we do this for different types of data, textual data, tabular data, and data from images. This is just an example of an output of our system. We are capturing the metadata from the top of this document. We're capturing tables. We are not tracing those graphs, but we can say that there are graphs here. and we're capturing information from using computer vision from these images. This is a type of technical document that's very common in the oil and gas or mining industry. So they, for example, drill holes into the ground and make observations. And from these observations, they plot these graphs, make these tables, and geologists would go in and do some narratives on what they found at each depth. So, for example, they would say something about sandstone here at the depth of between 15 meters and 75 meters, and so on. This kind of work in geology has been done over the past more than 100 years, and essentially millions, if not billions, of these logs exist in the energy and the mining sectors. So there's a deep wealth of information in these kind of technical documents, and it's very hard for users to get to when you have millions of documents. So what we do for our customers is to capture information like this and put it in a structured form in a database so that they can run queries. For example, if we are able to say that we have sandstone from this to this depth, then we have basement from this to this depth, then we can take all of this information from millions of logs, build a database so that these scientists and geologists can make more structured queries to find their information. They can make dashboards, etc. So we provide all these functionalities, and that also then includes search and chat. Looking at it a different way, just how the architecture of how the system works, it pulls documents from a drive, OneDrive, box, etc. Every document goes through an optical character recognition. And then we run our whole tool chain that includes classifying the document. So we index various things, index the document, what's in the document, what's on each page, apply visual object detection to detect certain things, to detect tables, and do some textual information extraction. So this was our platform until ChatGPT came. So obviously, ChatGPT threatened everything, and we had to move on. We had to learn, and we had to adapt. So what we did, we were just doing this, but now we started to do full index text search because we have 100,000 customer documents, for example. So we are indexing all of them, keeping all the text, the images, etc., so that we have all this information and we can provide more services on top of it. So what we did, we added APIs that data managers, scientists, analysts can use to integrate the data from the documents in their work and use it for their own machine learning. And then we also have started to provide chat using LLMs. The whole idea is we want the enterprises to be able to upload, say, 100,000 or million documents and be able to search in them, chat with them, annotate data, share any annotations with each other, and have these kind of more structured data functionalities as well, where they're capturing data from tables and more. So the idea is while chat is a key functionality, most of our focus has been to create structured data. So why do we do that? We'll get more into that. Mainly so that you can take these documents and create a chatbot, create a dashboard, because when there's so much structured data, you want to plot graphs, you want to see where something is in some region, or which element, for example, for mining is most common in one area compared to the other. So chat is just one way of getting information, but dashboards are another. And dashboards are difficult when all your data is in documents. So that's how we help enterprises make business decisions by building these dashboards with data coming from documents. And we do several things, like I was showing you, use information extraction to capture these kind of metadata. And this is just saying that, I'll skip this slide over. It's not saying much. Um, so before ChatGPT was BERT was there before ChatGPT. First thing we had to do is start using BERT to do more semantic information capture. And one of the ways we did that with our interface, users could select these text and classify it into categories, because that's what some of these enterprise users wanted to do. They wanted to see what is at each depth in geology. So they tagged data at different depths and classified it. They said, okay, uh, this is sandstone, this is limestone, etc. So we first used BERT to do these kind of classifications by using the text and getting the sentiment from them and assigning it to one of these different categories. That's just an example of how the user labeled it in our interface. They would go draw a box and say, okay, this is claystone, this is sandstone. And as they did that, we have built a point-and-click interface where from their labeling and data annotation, we automatically train models to do these kinds of classifications. And then once we've built a model, the output looks kind of like the way we trained it, of course. So this is just the output where this is an example of where we are combining computer vision with BERT. Computer vision finds this description and assigns it a depth in this document, and then BERT-based classification then says, okay, this is a claystone or something else. Sometimes, I mean, it has to be smarter than just identifying keywords, because sometimes it may say there was no claystone found. So in that case, we should not call geology a claystone. So BERT is able to do these kind of more semantic distinctions. That's just more examples. One of the things we do is we provide confidence levels, and then we provide a way for user to give more feedback, whether something is correct or wrong, and we continue to learn from their feedback. But at the end of the day, when we have run this on 10,000 or 100,000 documents, we can then create a structured database for the user. So so that's an example of the structured database where we have a description, we have a depth, we have a classification into different categories, and the confidence levels by which we got these classifications. And then we also store a link of where everything came from, because now if you have 100,000 documents, you'll create millions of these data points. Create a structured database of millions of these data points. But when you're finally making a decision, you find a key value. You found a row of interest. For example, you're looking for a sandstone at a certain depth. You can make that kind of query, and from once you have that query, and let's say you're making a business decision, then to support that business decision, you can go back to the page and look at the information, make sure it's correct, because hey, it's coming from machine learning. It doesn't. It won't be 100% accurate. So once you have it in a structured form, you can run many different types of queries. In fact, for mining customers, what we're doing is we're essentially saving their money in drilling, because they already have data from 100 years of elemental concentrations in reports. They are not in a database. They are in reports and tables and paragraphs, concentrations of elements in the areas they operate in. So if they need to make a decision on where to next dig for gold or lithium, I like to say lithium because while oil and gas may be going out of fashion in the long run, the whole green energy revolution is actually causing us to do more mining. When I say us, the world as a whole, because to support batteries, you need a lot of rare earth elements. So while oil and gas may be going down in long run, mining is going up, and still the fact remains we only have limited resources. So we need to make better decisions on where to get the minerals from, where to get the oil from, etc. So one of the other ways we're using BERT is to find conclusive sentences. So what users can also do in this platform is they can go tag some conclusive sentences in their reports. I'm still talking pre-GPT, so this is how we adapted pre-GPT to the BERT and everything, added more features to our platform to do more things like finding key sentences. So we trained BERT models to classify negative sentences and positive sentences. So the user marks these sentences, and then using our interface trains a model, and then they can dump their 100,000 documents, and so that they can always see for each document what is the most conclusive positive thing and most conclusive negative thing, instead of going through the whole document, because they may only be interested in documents with certain types of positive conclusion, and when they do this, they don't have to read the entire set of documents. And we found that with BERT, we used a BERT model for classification here to find what are positive sentences and what are not. And we found that by training with, say, 245 examples, we were able to get an 82% F1 score. So this is the example I was giving earlier. Once you have got all this structured data, you can make a dashboard like this. So if I click on a point here, this is not live, but this is not live. But if I click on a point, it'll tell me the elemental concentrations of that point. So this is a dashboard a mining company can use to make their decisions. Click at different points in the image to find the elemental concentrations and make better decisions on the basis of that. Now, there's a philosophical thing here. It's very hard to ask a question like this to ChatGPT. Look at all my documents and tell me tell me 3 points where the highest amount of gold is found. Typically, LLM is very limited in this way, where it will take a prompt and answer your question on that. If you're asking a question on 100,000 documents, there's this whole approach called RAG, or there are other methods. There are a couple of limitations here. These approaches cannot aggregate data, in the sense that to answer the question that, hey, tell me areas of 3 highest concentration of lithium. To answer this question, you have to look at every single document and find the lithium concentration, and then pick top 3. As much as we have seen, LLMs are not capable of answering these type of questions. So we are still taking this traditional approach with our customers. We're using either BERT or fine-tuned LLMs, or finding structured data separately for each document, putting it in a database so that these type of questions can be answered. Here's a recent work we've been doing with the government, but it applies to anybody. So let's say, so the idea here is testing. You acquire a piece of technology. Let's say you acquire, I'll give a silly example. Let's say, let's say you acquire a cement mixer or something like that, or a vehicle, and you want to test it. Now, you had asked somebody to build a cement mixer for you, but the problem is, you asked a vendor, as a government, you asked a vendor to build something for you. When they build it for you, you have to test it. What typically happens is it's very difficult to test such a thing, because the requirements on the system have been written sometime in hundreds of documents that have been exchanged back and forth with the vendor from the government. It doesn't just apply to government, also true for private industry. So these governments have gone, these documents have gone back and forth, and requirements written in emails, documents, etc., in paragraphs and tables. So now I tell a test engineer to test my cement mixer that I just got custom built from a vendor. So what are they going to do? They're going to go through these 500 documents and find what all do they have to test. So we have recently fine-tuned large language models to address this issue. So we are automatically capturing the uh, we're automatically capturing the requirements from these hundreds of documents and creating a table, and that table can be used by the tester to go through the requirements, because it's pretty much impossible for somebody to go hundreds of documents and find every single requirement and then start testing, especially when there are versions, etc. So we trained in collaboration with University of Illinois at Urbana-Champaign. We trained we fine-tuned a large language model to solve this problem, find requirements, and also find a parameter. So what is a parameter here? So we find, let's say, this new ducts will be minimum 18 inches and ideally 24 inches from the floor. So we have to tell the tester what do they have to measure. So what do they have to measure is the distance from the floor to the maintenance hole. Now this is interesting that the large language model generated this. It generated the word distance. This word is not there in this sentence. So this is a very neat and practical application of generative AI, where you take requirements and generate a measure for a tester, and so that they can compare it against the threshold. So that's the idea. Then we take information from descriptive documents where requirements are mentioned, and then create this testing table for test engineers so that they can go through it, and then they can also refer back to the documents to see where the information came from. Okay, I think that's all I have. These conclusions are a little dated, but in any case, we are using human in the loop AI to fine-tune LLMs, to fine-tune BERT, fine-tune other types of models to capture data from documents, and putting this data in structured form so that large-scale queries can be answered. I'll just give you a quick glimpse of what we have built. So this is our the front page of our user interface, where you can actually upload batches of documents. So each of these tabs is a batch. So that's straightforward. You just upload documents here. In each batch, you can see different documents. These are TIFF files, images, so they automatically OCR them and capture data from them. So we can see for this document, there were 8 pages, 13 values of data have been captured. And the document has been classified into these type of categories. So you can sort through these things so that if you want to get to certain type of documents, etc. But here's the key thing. When you go into a document view, you can see what we have done here. We're capturing some structured data here, even if it's in handwriting. So when I click here, it says that the total depth logger is 2462. This is correct. When it says depth logger, it read the handwriting, and it used the context to say that this is a total depth logger. These models are our own custom models. These are not GPT based. These are based on traditional machine learning, but they rapidly learn from the user. So how do they learn? You can say, yes, this is a total depth logger, or no, it's not. Either action trains machine learning models to capture the value of total depth logger from different these well documents. When you say yes, it is a total depth logger, it's not learning that when it sees the number 2462, it should be total depth logger. What it's learning is the context. If it appears in this type of context, it is a total depth value. But you also see we're actually using Microsoft Read API, but it's able to take that and then use our machine learning to capture some values of these attributes. There's a whole bunch of sort and filter things here. Now I can also do search and chat here. This is a development machine. I may not be able to demo chat today. Something broke this evening, and obviously it's Friday night at 11 p.m. I cannot bother a developer. But in any case, I'll show you how we have built chat into this. This might partly answer one of the questions I already saw in the chat. So let's say I want to find a document about ibuprofen. So I do that. I can go to that document. So this document is about ibuprofen. But I want to do more. Go to advanced search. Now, I narrowed down. I said ibuprofen. Now there are documents here for thousands of medicines, but I filtered the documents by name, and I only got documents for ibuprofen, the pages that describe ibuprofen. Now I can answer the question. I can ask a question, what is the dosage of adults? It gives me an answer. I'm not able to demo that. Like I said, maybe our GPU is down. I don't know what's going on. But the idea is that I ask a question. It will give me an answer from the documents that it has narrowed down on the basis of my search, as well as I can also narrow down on other things. I can give some attributes. I can say these two medications. I can give it some values where I could say, okay, I only want to look at medications where dosage is 200 milligrams or something like that. These queries, these are more structured queries that help me narrow down documents to a few, so that I can give that constant context to a large language model like ChatGPT or to Mistral AI or Llama 2, and then it answers the question. So this is a new functionality we have built. It's a very different way of doing RAG. We're not using machine learning to do RAG. We are using queries to narrow down the document on which we have to answer a question. That's all with the demo. Let me. Okay. Okay, I'm gonna go to some of the questions now. I have 50 GB of docs and PDF. I'm trying to make a RAG model with using BAI large embedding. I don't know what that is, but one of the things is my last 4 years I have been more working on building the company than working on technical on then with large language models. So I work with developers and data scientists who do that work. So I'm not the most updated on technical, but I'll still give you an answer for this. The model is not performing well. You have given an extensive prompt. It didn't help. I'll share my experience, Zafir. So far, we have not been able to find a good way to do RAG. So if you have 50 GB of documents and PDFs and you want a question and your expectation is it'll just give you an answer from those 50 gigabytes of documents, we've tried several RAG methods. We've tried LangChain, Llama Index. We haven't got good results. Maybe we are doing something wrong. I don't know. Like I showed you, we have taken a separate approach where we are narrowing down the prompt by narrowing down the documents to using users search criteria and some filters that the user can specify. That way we narrow it down and then they can ask the question. Going to Shiv Shankar, what is the best LLM based on benchmark? Well, as much as we have seen, nothing comes close to GPT Turbo 4 right now. But all of the other ones, Llama 2, Mistral, I think they're all in the same ballpark. We have not, some do better at some type of documents, other do better at other type of documents. That's just my experience. We've only tried Llama 2. We only use Llama 2, Mistral, and ChatGPT. So I think nothing is closer to ChatGPT for now. But then the other part of that is we have not really tried a very large Mistral or Llama 2 models. We've tried up to maybe 70 billion parameters. But OpenAI models, even OpenAI models are better than that from what we have seen. How to source billion parameters? I don't know what that means. If you can explain the question, it'd be great.
Yeah, actually, I too didn't understand that. So I got this from Google Forms. So
okay, no worries.
yeah.
Okay, Azhar, when trying to ensure the system outputs trustable documents, is the training fine-tuning the LLM, which is more important, or is it post-processing of LLM output? As much as we've seen, it's the fine-tuning on user, because ultimately every user will have their own uh, definition of trust and what they want from technical documents. So from what we have seen, fine-tuning is most important. But the second is a quick way to go back and check. You still need that. If you're making an enterprise decision, a big enterprise decision, you still need a way to check before you make that decision on where the data came from. Um, but post processing also plays a role. Sometimes even after LLM, the data is messy, and you can do post processing like checking of the ranges, etc. So that's also important. It's a good point. Sanjay, how to best use the number of epoch for fine tuning? Uh, I don't know. I think training deep learning models is still an art. Although I'm actually at NeurIPS today. I saw a very interesting paper. This is more, maybe you take it as a joke or maybe it's serious. I don't even know. But I saw a paper today where they asked GPT-4 to tell them the hyperparameters of the model, and they found that that approach beat a random search by a significant margin. So it was a funny thing, but uh, I mean, ultimately you have to do hyperparameter optimization, but in many practical situations, it's not really possible. Um, how to determine whether a model is overfitting in instruction-based LLM? I don't know. Sorry, I haven't worked with instruction-based LLM. I don't know if there's a specific meaning for instruction-based LLM. I haven't really, so it's hard for me to answer that. Is there a tool for inference of LLM model 4? For getting a good output, what should be the number of examples training? What is the, this question is too generic. I'm sure everybody will give you a different answer. And I have not personally trained LLMs, fine-tuned LLMs myself. So I'm gonna skip that. Label Studio in the backend? No. We have our own document labeling tool that we have developed. Microsoft Read API better than Google Cloud Vision? So this is a very interesting question. I'm assuming the question is for optical character recognition, but I'm not sure.
I think so.
So yeah, so that's funny. We tried all three. So far, we think AWS has the best OCR from everything we have seen. It's the most consistent, it also gives a good layout. If the text is in a certain layout, it preserves the layouts and the ordering of characters much better than any of these three. It also does the tabular text better, which Microsoft and Google are not good at. From what we have seen, they're not good at text in tables, while AWS is the best at that. So we are switching to AWS from Microsoft because of that reason. We process technical documents, and AWS is better at text that is all over the place in tables and images, etc. Although for handwritten, no, even for handwritten, from what we have seen, AWS is better. So I would use AWS, but I mean, but it can also depend on what you're trying to do with it. We are not using layout LM yet. We are using our own machine learning for layouts. Microsoft Recognizer seems to work very well. So yes, at a recent at a customer, we have replaced Microsoft, AWS, and Google with our tool. The reason is when Microsoft Recognizer or Google API or or AWS Tech Stack. When they work, it's great. When they don't work, there's very little you can do with it. The customer went with us because our interface to improve the accuracy was much better than those tools. But again, we are a startup. We just have few customers. They have thousands of them. But there are certain things we do better is to train on the data, train on their documents. Abhishek, can we chat on tabular data to get answer to specific queries? I think in the I think you can. From what we have seen in some of the latest versions, sometimes you're able to get good answers uh, from tables, but not always. But we have seen it good answers sometimes, able to somehow align and give an answer, probably for simpler tables, but I'm not sure how it'll do for more complicated tables. Yes, OCR spelling is always a problem. Spaces cause a problem. We haven't done something advanced for this yet. We are mostly relying on when we have to match certain words or something like that. We do fuzzy matches, fuzzy search. So we don't keep it so deterministic that it has to depend on exact spelling. And some of our models are using both character and words, so they're able to work with misspelled words as well. Can we store such huge unstructured documents in TBs as vector DBs and process them through LLMs? Well, there are tools out there to do that. Like I said before, we have not seen good results with it. And like I said, I also said maybe we are doing something wrong. So last couple of months, we've tried in different methods for vector database and RAG type approaches like LangChain. It works on few documents to narrow down the text, but when you give it that such a big data set, it's what we have seen, it's not very good. Okay. Happy to answer other questions. They don't have to be technical questions. Is there anything else I can answer?
Yeah, I think let me check if any questions. Another question from Deepak. So, do you think graph networks are better way of handling huge unstructured data or structured text data?
We have not worked with graph networks yet.
Okay.
So this is just elaborate on that. When you're building a product, you have very little, especially as a startup, very little leeway for research to do research of these kind of things, and we sometimes have to make decisions and pick one technology and build the product on it. Maybe we'll change it later. So I would be able to, some of these questions here, I would be able to answer much better if I was still a scientist working on these things. But because I'm running a company, I'm outdated on some of these things. So I'm sorry, I'm not able to answer them that well.
Okay, I think we don't have any questions in our chat. So another last question, like so he deleted. Anyway, so we don't have any questions now from YouTube chat. So I have one question, sir. Like as you know, like as you also mentioned, for a startup or small company, it's quite difficult to run huge amount of like big model on GPUs and do the training and all. So now my question is like how to choose model. For example, as you mentioned, like GPT-4 is best, but we have to pay for that. So we have to pay for the token per like whatever we are using. And then another approach is like whatever open source models are there, maybe Llama or Mistrals. So how to choose that actually? Because for those open source model, we have to fine tune and then do our own database preparation. So everything we have to do. So how to choose in between that, sir? Like maintaining the cost and all.
Yeah, it's a great question. I can answer this question from a startup perspective rather than a general perspective. What we do is we maintain a couple of models in-house on smaller GPUs, like 7 billion model. Customer-wise, we give them two options. One, you use ChatGPT, so our system will be connected to ChatGPT, so you can put your API, use that. We're passing them the cost, because what we are doing from them is bringing their million documents together, and they can filter, search, etc., and get to a point where they can ask questions. So uh, so we pass on the cost. Now there are customers, let's say a hospital, they don't want to. We don't have a hospital customer yet, so I'm making this up, but they won't want to send anything to ChatGPT. So our option to them is, hey, you get your own H100 or something. We'll put a 140 billion parameter model there and connect our tool to their GPU. So this is like an on-premise option. So again, but the key is we are passing the cost to the customer. As a startup, we can't. We're a different kind of startup, right? I mean, we are not OpenAI, we're a small company. Uh, so we keep our GPU footprint very small. It's mainly for our development and implementation. In production, we either our users use our tool as a gateway to do different things and also maybe ask questions. We'll send it to either ChatGPT or their own GPU. Does that answer your question, Sisha?
Yeah, I think so. Yeah, so thanks for the question answer. And we have another question. Last question. I think we can take. From Anmol, like, sir, I feel there is a lot of opportunity in India through this specially real estate records. Are you are planning to expand?
Oh,
Any
great question. We
some
would love to.
yeah.
We haven't planned to, but we would love to. We think that to expand in India, we need a
Okay.
partner in India, which I think is anyway US Indian government's requirement. Um, so to incorporate in India as a foreign entity, we would have to partner with somebody. So I'm actually very interested in learning about such opportunities. Feel free to reach out to me.
Okay. So another last question from my side is that, for example, we are, as you mentioned, like we can build our own model using Llama or those open source models. So, for example, we are having 5 tasks. So we are having 5 tasks where we want to give service to the customers, and then maybe like question answer, then summarization or different or maybe React also. Then like how to actually then we want to fine tune on top of Llama. Then how to actually deploy all those systems, like how effectively we can deploy and so that cost is also reduced.
Yeah, it's a great question. We are also working on figuring that out. And we think there's not much of an option here for us right now, except let's say, so what we would have to do, we would have to fine tune, say, 5 attributes, one for each, uh, 5 models, one for each attribute they're trying to capture. So you would, we would have to fine tune one, then fine tune second, fine tune third, fine tune fourth. And when we are inferencing, we have to just swap out models because that does not take too long, putting one model or another. It cannot be done for video, but processing documents, I mean, you can do such a thing. Very rarely somebody is looking to process documents in real time. Um, Typically, our customers will upload 1,000 documents, come back a few days later to check what happened. So yeah, it's a good question. It's a problem, right? If you have to do 5 different tasks and do a fine-tuned model, now do you get 5 GPUs? So yeah, it's a big problem. We are just swapping out models. We're at least planning to for now.
Oh, okay. So thank you. I think
Sure.
so. We don't have yeah, we don't have any questions in our chat box. So I think we can wrap up. Yeah.
Okay. Sounds good. Well, thank you very much again, Fisher. Thank you everyone for joining. Really appreciate it. I hope you found it useful. I hope to visit Assam sometime and meet some of you in person.
Thank you. Thank you.